that you don't really use them a lot. And this is kind of one of them. But you end up with y minus f of c equals f prime of c times x minus c. That's the equation of the tangent line at a given point. Okay? In other words, the equation of that tangent line is given by what I wrote. Let me see if I can shorten this up a little bit. Put this down. Where c is the x-coordinate of the point.
Okay.
In other words, in this particular case, c is minus 2. Okay? So that translates to y plus 2, which is the same as y minus f of c, c being the x-coordinate,
Okay.
equals f prime of c. Well, if I evaluate that at x equal minus 2, what do I get? F prime of c. Well, that's f prime, and we had to get this by implicitly differentiating. In other words, there's no way to explicitly differentiate that. You'd have to solve it for y first. So if we implicitly differentiate that, we can come up with y prime, and this is what they came up with. It is minus 2x over 2y plus 2. Okay? So what is y prime when x is minus 2 and y is 2? Well, if I plug that in there, I get 4 over 4, don't I? Let's see, f prime of minus 2 equals, or I should say f prime of 2 comma minus 2. Let me do it that way. In other words, my f prime in this case is a function of both x and y.
Yeah, that's...
So I want to write it like that. So it's f prime at that particular point. Well, when c is 2, y is minus 2. So f prime would be minus 2 times 2 all over 2 times minus 2. That's equal to 1 plus 2. So the slope at that point is 3. Go ahead.
So now she got 2.
I know. I'm trying to figure out how she got 2.
Let's see here.
In other words, did she implicitly differentiate that properly? Here, let's just implicitly differentiate this. I get 2x plus 2y, y prime, plus 2y prime equals 0. So now I have y prime times 2y plus 2 equals minus 2x. So now I have y prime equals minus 2x divided by 2y plus 2. Notice that is not what you wrote.
Yeah, that's my,
Okay? In other words, this line needs to go all the way under. Or, excuse me, this plus 2 is in the denominator. It's not being added to that quotient. Okay? So now, what is y prime at this point? Well, it's minus 2 times 2 divided by 2 times 2 plus 2. Ah, I got my signs wrong. No, that's the x, that's the y.
Yeah.
So I've got minus 4 over minus 2, which gives me minus 2 is my slope. So y prime, what's that?
Minus 4 over minus 2, would that be positive?
Yeah.
Okay. That's what you got. Okay.
Is that, did I do something? Minus 4 over minus 4 plus 2, which is minus 2. Yeah, that's a positive 2. Okay. So that's what she got for y prime at this point. Now she goes over here on the left and she says y plus the slope equals the slope times x minus 2, which is the x coordinate. So she actually said y, if we evaluate this, in other words, what I wrote, I believe is correct. Should be that right there. Okay, and y minus the function evaluated at 2. Well, what is that? That's 4 plus, yeah, that's 4 plus 4 minus 4 equals 4. Well, the function evaluated at 2 is clearly minus 2. Without plugging it in, I don't need to do that. Sorry about that. Okay. And my original equation said y minus the function evaluated at the x-coordinate. Well, the function evaluated at 2 is minus 2. Therefore, I end up with y minus a minus 2. So I end up with y plus 2. And that's how you get this y plus 2. Okay? And it's equal to the first derivative evaluated at 2, which is 2. That's where I get that 2. Times x minus the x-coordinate, which is 2. So that's how I get this. Okay? And now to find the y-coordinate when x isn't 2, but it's slightly away from 2. This method only really works when you're dealing with x values that are close to an x value that you know. In other words, this function's not going to work, this method's not going to work real well if I want to find the y-coordinate when x is 21 or 100. It's only going to work really well when this number is close to this number.
Okay.
In which case I have this equation applies. I have y plus the y evaluated at the point that I know it's true equals the slope evaluated at that point times the x value the new x value minus the old x value. So I end up with y plus 2 equals 2. That should be a plus 1, 0.1.
Yeah. Anyways.
Which means y is going, okay, see here, you got it reversed. or do you? In other words, it's supposed to be x minus c. Hold on a second. And the x coordinate is 2.1. Do you know, was this the answer she gave?
Negative 1.8, yeah.
All right. You get that by putting the proper sign on here.
Yeah.
Notice that if, indeed, it is x minus the original point. In other words, it's 2.1, this value, minus 2, which gives you a 0.1 there. 2 times 0.1 is 0.2. Then I got to subtract this 2 from both sides. That's how I get minus 1.8. So you wrote that as negative 0.1. It should be positive 0.1. 2.1 minus 2 is positive 0.1.
Yeah.
Okay. Now, if I want to do it when the coordinate is 1.9, well, I got all the work done, so all I have to use is this left-hand equation here. So it's y plus 2 equals 2 times 1.9 minus 2. And that does give you a minus 0.1, but it gives you a y value of minus 2.2. Okay? For the second problem, they're basically giving us everything we need to know. In other words, we know that we're going to use this equation, and I could take that f of c and move it to the right side if that's the way it's been presented to you, but this is the way my book lists it. Okay? They tell us that when x is 2, y is 3. So it's the same information they gave us right here. Right here, they told us that when x is 2, y is minus 2. So we know what the point that the original function passes through is 2 comma 3. Okay? And they also tell us what the first derivative is. So we don't have to do any of this. We don't have to implicitly differentiate it, substitute to figure out that the slope at that point is 2. They're telling us the slope at that point right there, is minus 2. So now you use the local linearization method to approximate what the y value would be when f is 2.01. Notice very close to 2. Well, here's my equation. Y minus f of c. Well, f of c is 3.
That's supposed to be minus 3 down there.
So it's y minus 3, not y plus 3.
Yeah.
Equals the slope at that point, well, they're telling us it's minus 2, times x minus the x value, 2. Well, the x that they want us to plug in here is this 2.01. So now we have y minus 3 equals minus 2 times 2.01 minus 2, that's 0.01. I'm assuming you did all your algebra correct here. And this should give us a value of 3 minus, that should be 0.02, not 0.2. Right? Minus 2 times 0.01 is minus 0.02. So that's how you get 2.98. All right. Let's look at the next problem. Write an equation of the tangent line shown here. Okay, that's easy enough to do. Let me move it over a little bit. When you have, this is almost the quintessential problem in differential calculus, is writing the equation of a tangent line given the function and a point. Okay? Well, first of all, the equation of any line is y minus y sub 1 equals the slope times x minus x sub 1. That's point slope format. Remember from pre-calc or algebra 2?
Yep.
It's used a lot more in calculus because usually what you have is slope and a point with an x and y coordinate. Okay? So the first thing we need to do is figure out the slope. Well, what is slope?
When you plug in the x values to the derivative.
First derivative. That's what first derivative means.
Yeah.
Is it's the slope. So let's take the first derivative. That's going to help us find the slope. What's the first derivative function?
Negative 3x squared.
And what is its value when x is 1?
Negative 3.
So that's the slope. That's our m.
Mm-hmm.
So let's go back up here. Yeah, let me erase some of this. We don't need this anymore. So the equation of this tangent line is going to be what?
Y minus 3 equals negative 3x minus 1.
And that's good. We don't have to simplify that. They didn't say put it in slope-intercept format. They just said give us the equation of the tangent line. There it is in point-slope format. Use this tangent line equation to approximate what f of 1.1 is. Notice that f of 1.1 is somewhere there. Not that easy to approximate, but we can do it. What's our equation? What's our general equation?
So y minus 3 equals negative 3x minus 1.
Yeah, let's first of all write it like this. Y minus 1, f of 1, equals f prime evaluated at 1 times x minus 1. Okay, so that's, in other words, the general formula is y minus f of c, c being the x coordinate, equals f prime of c times x minus c. Well, f of 1 is 3. You don't have to do any calculation for that. Equals f prime of 1, what do we come up with there?
Negative 3.
Times what?
1.1 minus 1.
Yeah. In other words, there's only one thing. That technically is x minus c, but c is our original point, 1. Our new point, x, is 1.1. In other words, the point that we're trying to approximate a value for. And it's important to know this is not an exact value. This is an approximation. If we knew the original function, which in this case we do, we wouldn't need to approximate. We would plug in 1.1 and figure out what that comes out to be. But sometimes that's not so easy to do. So in this case, we have 3 times, what's that, 0.1 times that. So our answer should be negative 0.9.
Wait. With that,
I got it wrong. That's 1. Negative 0.3.
and then wouldn't you carry?
And that's positive. Well, this is negative. That's positive. So what did I do?
And then you multiplied it by -3.
Oh, and then I got to add 3 to it. Yeah, sorry.
Yeah.
Sorry. So our answer should be 2.7. Is that the correct answer?
Yeah, I think so. That's what I got.
All right. So what's the actual value of f of 1.1? Well,
Is that when you were saying we can just plug into the original function?
yeah, and that's what I was just going to do here. Let's see. F of 1.1 is equal to minus 1.1 cubed plus 4. Do you have a calculator in front of you?
Yeah.
What did we come up with? 2.7? Which doesn't look very close to what this answer is going to be, but it's 1.1 cubed.
1.331.
Which means our answer, oh yeah, 1.331. So our answer is going to be 2.669. What do we come up with? 2.7? Yeah, that's not a bad approximation. You will learn later in calculus that if you keep, this is just the first level approximation. You can keep, once you learn about infinite series, you can add a second term, which is the second derivative, and a third term, and so forth. And every term you add gets your approximation closer and closer to the exact answer.
Okay.
All right. Let's open up this page here. Wow. Amazing that your teacher is spending so much time on this. That's not normal. This is the, I guess you'd call it the toughest part of differential calculus, I think. Well, I don't know if it's the toughest part. It's just the part that you don't use very often. You don't do local linearizations very much. All right. This is similar to the last problem. They give us the function. They give us a point. They want us to write an equation of that tangent line. You know how to do that? Shall we go through it?
Yeah, it's just.
Since this is such a critical capability, let's make sure you can do it without me telling you anything. What's the equation of that tangent line?
Would it be y minus 1 equals 2x minus 1?
Yeah. You got that by finding the first derivative, evaluating it at 1. That gave you a slope of 2. That's the slope of the tangent line. And using the point slope, we get that. Label a point on your tangent line with an x-coordinate of 0.9 as point A.
Olivia, tell him to turn that off.
Dad, turn the radio off. Jackson's up here. Working. Turn the radio off. Jackson's working up here, remember?
Is that a fair approximation of what they want here? Label, in other words, what I drew the tangent line.
Okay.
And they label a point that has an x-coordinate of 0.9. Now, I need to be a little closer to my x-coordinate from the point they gave me, but that'll do for our example. And label that A. Use your equation of the tangent line to approximate f of 0.9 by finding the y-coordinate of your point A.
So is that just plugging 0.9 into the tangent line?
Ah, I see what I did. I didn't quite draw my thing correctly here. Let's do this a little bit better. Let's draw the tangent line. But 0.9 on the x-coordinate is about there. What I don't know is the y-coordinate. I mean, I know what it is based on that, but if I didn't have the function, we'll just call that y. Okay? And we want an approximation of y. So, remember what our equation is. Y minus f of c equals slope, equals f prime evaluated at c times x minus c. I think you probably need to have that memorized in that form. Because as long as you know that, you're going to be able to figure out all of these problems. Okay?
All right.
What is C?
Wouldn't it be 1?
Yes. Okay, so we get the approximation is y minus, well, f of c is also 1. The y value at c equal 1. F prime of c, we've already figured out, is 2. X minus 1, notice that that's the equation of the tangent line. Exactly. Only in this case, since I'm approximating when 0.9, I need to put in 0.9 for x. And that's going to be my approximation. You know, I wonder if that's always the case. In other words, is it always the case that if you can come up, I think this problem is trying to illustrate to us that if you come up with the equation of the tangent line, that's the starting point for doing a first linear approximation of another value for x. In other words, all of these questions on linear approximation could start from the equation of the tangent line. So what is this? Y minus 1 equals 2 times negative 0.1, so that's negative 0.2. So y equals 0.8. And the one thing we can see from our picture is that y is definitely lower than 1. So that answer makes sense. And it's always a good idea to check that, to make sure that it makes sense. And if you actually plug in 0.9, you'll see that y would equal to 0.81. So again, this is an excellent approximation for a long time, this is the way they found values that they didn't know how to solve for. Okay, label a point B that has an x-coordinate of 0.9. What's the actual value? Well, we just decided that that was 0.81. Use the same tangent line to approximate f of 0.6. How accurate is your approximation? Well, what's the approximation of, in other words, if I'm starting from this, what's the approximate value of y when x is 0.6?
Is it 0.2?
Which means is that when I get to there, they're saying that the approximate value of y is 0.2. Well, if I plug in 0.6 into the function and actually figure out what f of 0.6 is, I get 0.36, not 0.2. I'm not even close. Okay, and what that tells you is that this is only good for when you're really close to your original x value. I can't use the equation of the tangent line at that point, 1, 1, to approximate the value of y when x is 0.6. It's too far away. It's not a good approximation. Now, if I use the full approximation, I'd be able to. The full approximation you haven't learned yet, but you don't get that until Calc BC.
Okay.
Okay. Again, more problems on linearization. That's okay now that we know how to do it. Approximate the square root of 26. What we know is the square root of 25. Well, 26 is close to 25, so we can use our linear approximation method to do it. What's the general equation?
Y minus 5.
Well, let's call 5 f of c.
Y minus f of c equals f prime of c times x minus c.
Yeah, that's the one to remember. And the thing to remember is that c is the x coordinate. So y minus 5, because f of 25 is 5, according to this point. What's the slope evaluated at 25 equal to? What's y prime, first of all? If y is x to the 1/2, what is y prime?
Would it be 5?
Well, let's first of all figure out the function. What is f prime of x? Remember, f of x is x to the 1/2. So what's f prime of x?
1/2 x minus 1 to the negative 1/2.
Right. And now we want f prime of c. So f prime of 25 is what?
Would it be
Okay, so all I did was plug in 25 for x, took the square root of it, it came out to be 5. So that's how I ended up with 1 over 2 times 5. Okay, so the slope at this point, remember we're using the slope at this point, not the slope at this point. We're using the only slope we know how to get, which is this one. At that point, the slope is 1/10. Now, what do I plug in for x minus c?
Be x minus 25.
Plug in an x. We're approximating the square root of 26.
So, root 26 minus 25?
Just 26. In other words, this was giving us the square root of 25. We want the square root of a number very close to 25 is 26 minus 25.
Okay.
Okay? So that's why this is such a key thing to remember. If you can start with that general equation, you can figure out everything else as long as you understand that c is the x-coordinate of the point you start with. I can't call that x because we have this x here. This is the point that we're going to approximate. This is the point we're going to use that's not this point. Okay? So I end up with y equals 5.1, which is at least on the correct side of that. In other words, 26 goes to the right. So 26 is about right there. We can see that the y value is greater than that. And in fact, if you looked up the square root of 26, I'm sure it would be very close to 5.1. I have a calculator here. Oops. 5.099. It's actually pretty incredible how accurate these things are. Our real value is 5.099. And we came up with 5.1 just using an approximation method. Is this whole lesson on the linearization? Because it's about to be if we keep going.
Yeah, I assume so.
Okay, that's fine. I have no problem with that. I just don't want to, in other words, you sent me 4 pages. We're only on the second one, and we only have 15 minutes to go. So if there's some really important stuff on the other pages you want to cover, let me know. But
on the third page, I think there's like some optimization.
Okay.
If you want to do, we can do 14.
All right. It says use a calculator to answer the questions. How many people have become sick by the 10th day? Where am I going to plug in 10? In other words, answer A is f of 10. 10 is x.
Okay.
X represents the time and days since the sickness started. And x is the only variable in this function. E is not. E is a constant. E is like 2.71. Think of E as kind of like pi. It's an irrational number that's approximately 2.71. Okay, so it's a constant. So it's easy enough to figure out what f of 10 is. Just plug that into your calculator and do the math.
Okay.
Okay. How fast was the disease spreading on the 10th day? Well, what does that mean?
Is that the rate of how fast it was?
Yeah, rate means what?
The slopes, you're going to find the derivative?
Rate means derivative. When you hear the word rate, Well, and you made it up. It wasn't even in this. But when you say how fast, think of how fast a car is going. That's its rate of speed, its velocity, and that's always first derivative. So when we're looking for how fast something was spreading, we're looking for f prime of 10. In other words, we have to take the derivative of that function and evaluate what its rate of change was when x was 10. Now, taking the derivative of that function is not particularly easy. We wouldn't want to do it manually, and that's why they said use a calculator to help, because you can use numerical derivative to get the derivative of that and then evaluate it at 10.
Okay.
Okay. C, find the maximum point on f prime. How do we find the maximum on f prime?
So once you found that derivative,
In other words, I'm going to take a shot here and draw f. Let's see, if I were to draw f, this is a logistic function. And logistic functions typically look like that. And that is a horizontal asymptote on top and bottom. Okay. But that's the function. That's this function here. That's not f prime. F prime starts with a low positive slope, goes to a high positive slope, goes back to a low positive slope. So if I wanted to graph f prime, I said it started out in other words, this is f prime here. It starts out at a low slope, goes to a high slope, and then goes back to a low slope. Right? In other words, if I look at this logistic function here, starts out at a low slope. These are low slope numbers. These are high slope numbers right there. And these are low slope numbers, and they're all positive. In other words, it never goes negative. And what they want is that point right there. What is the x-coordinate of the maximum of f prime? How do I get the x-coordinate of the maximum of any function?
so the derivative equal to 0?
Take the derivative of this function and set it equal to 0. When I take the derivative of this function, I'm taking f double prime. Right? If I take the derivative of f prime, they want the maximum of f prime. So I have to take the derivative of f prime, set that equal to 0, solve for the x-coordinate. Again, that's something you can do on your calculator. I could do on Wolfram Alpha. I don't think it's important that we do it as much as you understand what we're doing.
Okay.
What does the x-coordinate represent? Well, in other words, once we've done this, find the maximum point on f prime. What does that coordinate represent? Well, if I go back to the function, that would be somewhere right in there where that slope is the steepest. I don't know if that slope is the steepest right there, or maybe right there, or perhaps right there. I don't know precisely by looking at the original curve where the slope is the steepest, but I know that if I take the derivative of it and set it equal to 0, I'll find that point. This is where it gets a little complicated because you're finding the maximums of a first derivative curve, not the maximum of the original function. Notice the original function doesn't have a maximum. Well, it kind of does, I guess. I guess that it approaches that. It never reaches it, but approaches that line. But it's an always increasing curve. In other words, it never decreases. So there's no maximum like the first derivative has. The first derivative has a maximum because then it goes back down. Okay, so they said, what does the x-coordinate represent? That's the place, I guess if you had to put it into words, that would be where the rate of change, the sickness is spreading the fastest. That's the day where the sickness spreads the worst. Remember what x is. That's represents the time and days since the sickness started. So the rate of change is the maximum at that x-coordinate. What does the y-coordinate represent? Exactly what that rate of change is. In other words, when we find this maximum right here, we're finding this point right there. Remember that vertical axis is the rate of change. So the disease is spreading the worst after X number of days, and its rate of spread is the y-coordinate of that. Finding a maximum or minimum with a calculator is not allowed on the AP Calc test. Okay, which means you would not get this problem on an AP Calc test because there's no way are they going to expect you to take the first and second derivative of that manually.
Yeah.
So how many people have caught the disease when the curve is the steepest? Well, the curve is the steepest somewhere in here, and it's at this point, x. That's where the curve is the steepest. Remember, steep is slope. That's the same thing as saying, where does the curve have its maximum slope? How many people have caught the disease when the curve is the steepest? Well, at this point in the question, we have figured out what x is, where the curve is the steepest. So we can go back to the original function. Remember what f of x is. F of x represents the number of people who have become sick. So it's f of whatever this x turns out to be. We didn't actually calculate it because I didn't want to take the time, but whatever that number of days is, plug it into this formula, the original function, and it'll tell you how many people have gotten sick. That's what f of x is.
All right.
So that's how we answer D. Why would the slope of the curve decrease after a period of time? They're talking about the original function. Notice that as we go to the right on this logistic function, the slope decreases. In other words, if I blow this up really big, I have as the curve approaches that horizontal asymptote, the slope decreases, right? So I have a fairly steep slope there, and not as steep there, and then gradually it's still plus, but it's less plus By the time I go way out to the right, it's almost zero. It's just barely above zero. In other words, it's always increasing, but it's always increasing towards this upper limit. Why would the slope of the curve decrease after a period of time? Well, if it didn't, it would go right through that. The nature of a logistic function is that it starts out exponential. In other words, this part of the curve, population growth is a good example of logistic growth. Population growth, when you have a small population, grows exponentially. It grows, it makes it look like it's going to go like that forever. But what happens is as you reach a certain limit, the resources are limited. There's only a certain amount of food on the planet. There's only a certain amount of space on the planet. So it can't grow exponentially forever. And what happens is it tends to flatten out and approach the upper limit. And this is just a process in our world that happens, and it doesn't matter what you're talking about, whether you're talking about humans or wolves in Yellowstone. I mean, you could put a dozen wolves in Yellowstone that has no wolves at all, and it's going to grow exponentially at first. But once the wolves reach a population of who knows what, 10,000 maybe, at some population their food isn't enough to keep growing exponentially. So they turn to flatten out, and frequently there will be an upper population limit, and maybe it's 10,000. Maybe that's the upper limit on wolves in Yellowstone. When they reach that level, they can't really grow anymore, or they grow very slowly. As we go to the right, we're still growing, but we're growing very, very slowly. And we're approaching our upper limit based on the natural resources of the area. I don't know, what do wolves eat? Rabbits? Maybe they've eaten all the rabbits and they can't keep eating rabbits, so they can't keep multiplying. And that's why most things in the real world, including bacterial growth, if you're talking bacterial growth, it's limited by the size of the petri dish. In other words, as soon as it hits a very large number, it fills up the petri dish and it can't keep growing. So bacteria grow more like logistic functions than they do exponential functions. Same with population, same with most everything.
So for E, what would you say? Just
because as the number of people, in other words, there's only an isolated population of 4,000, right?
Right.
So you can't have any more than 4,000 people get sick. So as you approach, in other words, when 3,900 people get sick, you can't have that many people getting sick each additional day.
So the number of people getting sick decreases.
Yeah, the rate at people getting sick decreases, not the number. The number of people that have gotten sick, in other words, if I have 3,900 people getting sick, say 3,900 people have gotten sick, and 50 people per day, 50 new sicks per day, well, I'm going to run out of people real fast. In 2 more days, all 4,000 will have gotten sick, and I won't be able to have any new sick people anymore. So the rate of people getting sick decreases as I approach my upper limit. It's just the nature of the world and logistic functions. There's a period where the maximum rate is hit, and then that tends to slow down.
All right.
I know I'm not answering your question fully because it's a little bit hard to answer, but as long as you understand what's going on, you can put it in whatever words you want.
Yeah.
When was the rate of the spread of the disease increasing the fastest? When was the rate of the spread of the disease increasing the fastest? Seems to me that that's the same question as C. I unfortunately have a 1 o'clock appointment that I have to go for, so
Yeah.
I can't talk anymore about that, but this may actually be the spread of the disease is the first derivative, so the rate of the spread would be the second derivative. That's where the second derivative is the steepest. So that's really where the third derivative is equal to 0. So
Okay.
f would be, the third derivative would be equal to 0. Okay?
All right.
All right, Jackson. I will talk to you next Friday.
All right. Thank you.